Part 4, Euler's equation. E to the ix is equal to cosine x plus I sine x, and why you should believe it. So here's how you derive this. I checked it out online and this works. Step 1, get your power expansion for e to the x. And there it is. Step 2, get your power expansions for cosine x and sine x. Now that you have them all together, replace x with ix. I think you can do that. Okay, there's that. And then remembering that I squared is equal to -1, notice that the e to the ix term has some negatives and some positive terms in it. That's good because apparently so does cosine and sine. Also notice that we have some real and some imaginary parts of e to the ix, so why don't we just organize them together? Notice this and declare victory. So the important thing about Euler's equation is what did he do after lunch? And of course I'm joking, but see, that's what I read online, and that makes it sound, I think, a little bit too easy and not nearly fun enough. And where did those power expansions come from? Those power series for e to the x, cosine x, and sine x. Are there any more? And do they work, and why? And that's the Taylor series, and that's part 5. But our friends are restless. They want to solve a problem. We had fun solving this problem. We did that earlier, and then we saw that this is not true. -3 to the natural log 4 is not equal to -4 to the natural log e. Why not? They have the same magnitudes, that's true, but they are in the complex plane. They have real parts and imaginary parts, real apples, imaginary apples, directions, different, same magnitude, but different directions on the complex plane, and we want to rotate one of them to the other. Can we do that? Do we know how to? Does this guy know how to do that? Does Euler's equation do that sort of thing for us? That question motivates us to take a deeper look at these power series expansions. First, I want to investigate whether or not this is really true. Does e to the x equal that? Well, does it for x equals 0? Well, let's find out. It does. Well, does it? I'm a little unsettled. Isn't that 0? No, it's not 0, because 0 to the 0 is 1. And 0 factorial is also 1. Fun fact. So it works because e to the 0 is 1. How about e to the 1? What do you get? Plug that into your calculator. 1 to the 0 plus 1 divided by 2 plus 1 divided by 6 plus 1 divided by 24 plus 1 divided by 120. That gets pretty close. If you plug in more and more terms, I think it took me up to 10 to get a good value for e. I like it. But what about x equals 2? What do you get then? Well, again, you got to go to your calculator, and again, I had to go to 10 terms instead of the 6 that are shown here, but it works, okay? It works. It works. What about those guys? What if we plug in x is equal to 0? Does that work? Yes. Yes, and yes, and yes, and yes. How about x is equal to 1? Does that work? And again, this is a kind of a, I was surprised. I was thinking this might not, but it did work. It did work. You got 1 on the top there, cosine. I never know if to do cosine or sine first. You got 1 minus 1/2 plus 1/24, and then I carried it out for 10 terms, and it worked. Cosine 1 in radians. Sine 1 worked too with the positives and the negatives. Coming to an agreement. Coming to an answer. I love it. How about x is equal to 2? Does that work there? Again, it took more terms, but I got an answer there. Sometimes positive, sometimes negative, very much like the cosine function there. How about x is equal to pi? Can we plug in? No reason we can't plug in pi, and it works. Again, I had to carry it out for more terms than you see here on the page for 10 terms, thanks to a spreadsheet, but it worked, and it convinced me that it worked, but can we convince these guys that it's useful? These guys want to do something fun and useful. How about we take Euler's equation and plug in x is equal to pi? What would we get then? Well, the cosine of pi, you know that, and the sine of pi, that you know that also. You do know that, don't you? That's right, that's e to the I pi is equal to -1. That's fun and useful, and it's already it's even something that we sort of already knew from part 3. I think it was part 3 where we said this. The natural log of negative rho is equal to natural log of rho plus I pi when rho is greater than 0, because your calculator won't let you take the natural logarithm of a negative number, but we can with complex numbers, and so yeah, e to the I pi has to equal to -1. There's that, but it's weird. It's weird because I started out by talking about negative being a direction. Is I pi also a direction? Well, I and pi are directions on this complex plane there. So is going negative like a pi radians revolution? Is that what? That's exactly what we're saying, which we'll get to it with greater formality. Give us a second here. Because our two friends, once we let them have, now they're going to be critical. Look at this equation. This is nonsense. E to the x, I'm not sure about this I business, but e to the x does this. It goes shooting off to infinity. What about sine and cosine? They stay at home, bouncing around. Also, in part 3, I said that this is an angle. This is an angle, so e to the I, that kind of looks like a magnitude. And if you don't believe me, again, I'm not sure about this I business so far, but we already said that e to the 2 is even greater than 7. That's not an angle. That's a magnitude. It looks like a magnitude, but you're telling me that if e to the I pi, or e to the I times 2 is equal to cosine 2 plus I sine 2, then we would have a angle. Then we would have an angle, a point that we could put on this circle on the complex plane. So that doesn't look a lot. So we're going to have to use the Taylor series. We're going to have to use the Taylor series on several equations. The first one OWL presents to us is the expression, the equation f of x is equal to e to the x. There's a good one. There's our Taylor expression, and I didn't talk about it in great detail, but I will here. It really has two different parts. The first part is a derivative part. So we'll take e to the x, take that function, the 0th derivative, you could say, and evaluate it at point A. What's A? We'll find out later. Anyway, we agree that e to the x at x is equal to A is equal to e to the A. We agree on that, don't we? Okay. And then we have x minus a to the 0th power over 0 factorial. We'll have to go kind of quickly here, but you can check these. I think you can even read them too. So e to the x is equal to e to the a because x minus a to the 0th power is 1. All right, I like it, but now we're going to do something crazy. We're going to say that a is equal to 0. So e to the x is equal to 1. We're going to say we're going to assign a is equal to 0, and this is going to make life a lot easier. On to the first derivative. The derivative of e to the x is e to the x. We knew that. At a, that's e to the a. Okay, and here we have again x minus a, this time to the n equals 1 power over n factorial, where n is 1. We'll do a lot of these. You'll get used to them, I promise. I know it's a lot. Anyway, we have here e to the a times x minus a at a is equal to 0 gives us that. Just x. The second derivative. Not surprising, the second derivative is the same thing. That's what makes e to the x so awesome. Then we have 1 over 2 factorial times quantity x minus a to the 2th. And that's that. And then at a is equal to 0, that's this. And we see here we are building that power series. The third derivative gives us that. We can then write it out. Evaluate it at a is equal to 0. We demanded that x is equal to a, and then we set a to equal 0, and we have a power series for e to the x, which is a good expression for e to the x, which we already tested, so that's where it came from. It came from the Taylor series. Now, what the Taylor series is and why it works, that's more of the next video. Again, we're just trying to have some, we're trying to add some we're just trying to have fun with Euler. I said his name wrong. I was trying to do this whole thing without saying his name. I'm sorry I said his name. I don't know. We're just trying to see what it does. Can we really believe this? Anyway, that's what the Taylor series gives us, though, is a way of writing out a power series for this continuous function at a is equal to 0, but it also works not just near a is equal to 0. But for this case, it works for a is equal to something far away from 0. And why? We'll talk about the ratio test, and we'll talk about convergence more in part 5. All I'm talking about here is those are some nice derivatives, you got to admit. And the Taylor series is about derivatives and powers and factorials. Who doesn't love a good factorial? Let's remind ourselves about derivatives, about the sine and the again, I don't know ever which to put first, sine or cosine. We know that the derivative of sine is equal to cosine. The derivative of cosine is negative sine. Here is sine at 0. The slope of sine at 0 is 1. That's equal to the cosine of sine 0. The slope of sine pi over 2 is 0. The value of cosine pi over 2 is 0. The slope The slope of cosine pi over 2 is -1, and the value of sine pi over 2 is equal to +1, so the derivative of the sine is equal to the cosine, and the derivative of the cosine is the negative sine. One final example. And Yellow Tiger has this, a function to write out a Taylor series 4 or 5. So let's get to it. N equals 0, so that's the 0th derivative, that's sine x at a, so that's sine a, got it? And then we have 1 over 0 factorial times x minus a to the 0th power, so that is equal to 1, that's sine a, and then we say a is equal to 0, so that is 0. So much for the first term. On to the second term. The derivative of sine is cosine. And then we have that expression of 1 over 1 factorial times x minus a to the first power. So that's cosine a times that. If a is equal to 0, that is equal to x. Okay, on to the second derivative. Derivative of cosine x is negative sine x. And we'll let x equal a at this point. And then we have 1 over n factorial quantity x minus a to the n. There it is, but the sine of 0 is 0, so it goes away. The third derivative takes us back to cosine, this time a negative. That's where the negatives came from. Oh yeah, we had negatives, and that's where the negatives came from. And when it's negative cosine 0, the negative of cosine 0 is -1, and then we have negative x cubed over 3 factorial when you work it all out. Kind of an ugly way of writing out that series. Basically what we're saying is if you're the sine function, you are in to being odd. Owl is more serious with the cosine function. Here we go again, the 0th derivative, cosine a, and then that's just 1, and if a is 0, then cosine 0 is 1, and the second derivative, negative sine of x at x is equal to a, and then we're familiar. See, I told you get a little bit used to these things, and the negative sine of 0 is still 0, so that goes away. See ya. How about the second derivative is negative cosine a, and that's not a problem, and that other term there is not a problem at all, but we have a negative here, a negative 1 over 2 factorial x minus a squared. A negative 1 over 2 factorial x squared, love it. If that's the cosine, though, the third derivative has to be the sine a, and that goes away when a is equal to 0. Still not sure why we're allowed to let a equal 0. It seems like we're kind of cheating. We're losing lots of terms here. If it works, it works. And there's our series expansion for cosine x. Again, when I was reading that textbook, it said that the Taylor series will allow us to draw out a power series expansion that's good around a value like around a. But our values were good even away from a for the sine and for the cosine function, which makes me suspicious. Anyway, there's the derivatives. I feel like this is all about the derivatives being nice, playing nicely with one another. And what's that? Tiger has another function for us to take a look at. Oh yeah, we're going to have to raise e to the gamma x power, not just e to the x, where x is equal to a bunch of different things, but e to the gamma x. You ready? We can take the derivative of that. The derivative, this is the 0th derivative though, so we start just with e to the gamma a. We're going to let a equal 0 again, right? So that's easy, that goes away. The first derivative, it kicks out a gamma. It kicks out a gamma. We are familiar at this time with what? 1 over n factorial times quantity x minus a to the n power is equal to. That's not interesting anymore, but there's a gamma to worry about. E to the 0th power is still, well, it's very tidy. That's what it, and it's almost too good for me to believe that it's okay to do that. But if it works, it works. Anyway, there's the second derivative. We kick out another gamma, so it's gamma squared now. We've got a gamma squared term, but we don't have much else. But I guess we still have that x squared over 2 factorial. Yeah, looking at that, yeah, we've got that too. Maybe I should go a little slower. Third derivative, gamma cubed, x cubed over 3 factorial. We certainly recognize a pattern at this point. We can get tidy, get the series, and again, examine and admire our derivatives. Especially, that would be especially symmetric if gamma was I, don't you think? I agree, and it's all thanks to the Taylor series, which somehow magically connects derivatives and powers and factorials, and is our key to e to the ix is equal to cosine x plus I sine x. We still have that problem to worry about with the rotation. Anyway, here's a strange grid. Since I said that the Taylor series is connecting powers and derivatives, let's do that again. That's I to the n power, and that's the n derivative of cosine and sine. And you didn't have to ask. It's evaluated, of course, at A. Here is a slightly different way of writing I with zeros and negatives. We're trying to show the connection here, and a connection we certainly see, especially when A is equal to 0. Well, that's a pretty good, but what is it? They're connected, but what are they? I'll tell you what they are. They're rotation. If n is equal to 1 real and 0 imaginary, then n is equal to, that's the blue line. That's at n is equal to 0. That's the blue line. What's the red line? It's the derivative. The derivative is a rotation, not speeding up or slowing down, changing direction. Can the number of apples change if they're not getting bigger or smaller? Yes. If you have the complex plane, here is n is equal to 1. Well, the blue line, what's that? Well, we've got 0 real and 1 I in the imaginary plane, but what's its derivative? -1. Its derivative is -1. You see, that's what we're doing. This shows a rotation. The derivative is always perpendicular to the vector. And okay, you say that might have worked for A is equal to 0, which was so convenient, but does it work if A is equal to pi over 4? Well, good question. Good angles. We can use the radian button on our calculator and find out all these things. And what do we find out? Well, we find out that at n is equal to 0, where's the blue vector supposed to? The n is equal to, that's blue. You're blue if you're at about 0.71 in the x and about 0.71 in the tiger direction too. That's the blue vector. And then what's your derivative? Your derivative is perpendicular to you. It's in the negative x direction, but still in the positive I direction, I/y direction. This might take a little bit of looking at, but what I'm trying to say is that the derivatives are always perpendicular to one another, which is exactly what you need if you're going to be a rotation. One more example. This time a little bit less symmetric. You could say, let's use A is equal to pi over 6. There's a good one. We know about pi over 6. We know about 30 degrees. So we'll move a little bit slower here, but you're at 30 degrees here, or you're at pi over 6 radians. So that's the blue vector. It's positive in the owl real direction. It's positive in the tiger direction too. What about its derivative? Its derivative is perpendicular to it. Its derivative is negative in the owl direction, positive in the tiger direction, and it goes around and around and around like that. And that's what we meant when we said that exponents and imaginary numbers do rotation. And we're done, except that I forgot it. Do you remember what I forgot about? I forgot about that rotation problem. What can we multiply by this one vector? Oh boy, can I even say this? What beta will turn a -3 to the ln4 into -4 to the ln3? And we need to rotate here. They've got the same magnitude. So our job is to find beta. Can you? Do you want to? Anyway, here's how we wrote out our vector positions of magnitude and direction. The direction is what we're super interested in here. The first angle there is 1.9 radians, and then the blue one, the blue is -4 to the ln3, that's 2.8 radians. So we can find the change in radians. The change in radians, and the rest is easy. Again, if it works, I'll buy it. Like a used car, if it runs, I'll buy it. If this will get that to the other thing, if this will change from pink to blue, we're good. Will it change us from pink to blue? Well, what can I write out for e to the I 0.905? What can I write out for that that'll multiply that and turn it into that? Well, cosine theta plus I sine theta. That's the ticket. That's our ticket out of here. And if you multiply those together, should I mention the term FOIL? Someone's going to get mad if I say FOIL, but don't forget that I squared is -1, and yes, you'll get it, and you'll be good, and you'll be happy, and you'll be relieved that we can turn one vector into another in the complex plane. You'll fully accept that exponents and imaginary numbers rotate. Why do they do that? Well, what is special about an exponent? It is proportional to its own derivative. But what's special about d dx of e to the ix? It is perpendicular and proportional, but perpendicular to its own derivative.